computer. Okay, welcome back everybody for the final lecture in this series. So Sandipan, it's up to you.
Thanks, Anindo. Okay, in the last two lectures, after last two lectures, we are in a position to actually impose constraint on effective field theories directly from safety axioms. As I said before, safety axioms are completely well understood, and so this alternative perspective of effective field theories as theories in ADS with large ADS radius, it is actually it's actually a powerful idea because of that. In fact, this whole approach conceptually, it's conceptually very clean, and I actually find it very satisfying. However, it is actually not a very new idea. In fact, this general idea has been around for a while now, but for some reason, it's not yet mainstream. So hopefully that will change at some point. So let's just begin.
I mean, Sandipan, one of the reasons why, I mean, isn't there a question that if you have a consistent quantum field theory in flat space, it is not necessarily true that you can always consider the same quantum field theory in ADS space? I mean, because there are always extra couplings that you can turn on, which may be necessary to make the theory consistent in ADS or whatever. And then, I mean, also I think we had a brief discussion about it. I mean, isn't that the reason why this has not become a mainstream idea as yet?
I don't think so, because like generally, like when that happens, you can actually tell. So basically, like you can always check whether the theory that you started with in flat space, if it has a proper ADS version or not. So generally, like this kind of analysis, the goal is to actually derive constraints which are irrespective of all the other couplings. So if there are other couplings that you need to turn on when you are in ADS, when you take the flat space limit, generally like they will always vanish. Let me give you an example. Like for example, so when you have higher derivative interactions, for each flat space interaction, there might be multiple ways you can write down the ADS version. So because like the derivatives they don't commute, but the difference will always be suppressed by some power of 1 over RADS. So it's possible that you can get different bounds in ADS, but when generally when you take the flat space limit, the difference will disappear.
I see.
But as you said, there is a very specific example that I have in mind, which actually can ruin the flat space limit in some sense. I'll actually discuss that. It's basically whenever you have interactions which are
positive mass couplings, yeah.
Yeah, so then there might be issues, but I don't think they are actual issues, but I'll discuss that. It's basically those problems are it's kind of telling you cannot actually take the exact flat space limit, but there are some issue with the order of limits.
Okay.
Okay, so with that introduction, so let me start with arguably the simplest effective field theory I can think of. It's basically a scalar effective field theory in ADS. So the effective action is the following one. We have a single scalar field in D spacetime dimension. Kinetic term, a mass term, and all high derivative interactions with 4 fields. And this is everything I'm going to say. Everything is valid, definitely valid for d greater than equals to 4. Now let me state the assumptions. First assumption is, this is just a simplifying assumption, which I'll relax. So the first assumption is there is no dynamical gravity. But this can be included easily in the analysis. I'll discuss that as well, obviously. The second assumption is I'm going to treat this effective field theory at tree level. So which is implemented by taking mu to be small. So everything will be computed at the leading order in mu. So where this is mu. This is mu. Again, I'm going to take radius to be large. So whatever the cutoff scale of this effective field theory is, that quantity is large. But important fact is, so generally in the first lecture, I mentioned that these higher derivative interactions appear when you integrate out heavy fields. So, and in that case, this lambda k coupling constants, they are expected to be suppressed by higher and higher powers of the cutoff scale. But I'm not going to assume that. I'm just going to take this effective field theory as given and try to find similar statement about lambda k from the analysis. I'm not going to impose by hand that the high derivative interactions are suppressed by some by the cutoff scale and the coefficients are order 1. I'm not going to impose that. So no constraint on lambda k to begin with. However, I'm going to assume that they don't scale with radius. That's the only thing that I'm going to assume. So these are rather general assumptions. The next thing is I'm going to assume that there are no light particle with spin 2 or more than 2. And also note that there are these dots. So they contains all the other interactions. For example, this dot may contain a phi cube interaction. So these dots can include many other interactions as well. So basically, the statement that I would like to make at the end of the day, they should not depend on any of these additional interactions. And there are some subtlety with, particularly for this phi cube interaction, that I'll discuss at the end. And note that there can be other higher derivative interaction. Especially when you have like more 12 or more than 12 derivatives. So this is not the only 4 derivative interaction. This is not the only 4 field interaction that you can write down. So these dots includes those other interaction. So in other words, like when you have a lot of derivatives, when you have like less than 12 derivatives, all the interactions, all the four field interactions with derivatives that you can write down. After performing some integration by parts and using equation of motion, you can always write them in this particular form, that phi square box k phi square, this particular form. But when you have a lot of derivatives, you can it's easy to show that there are interactions that can never be written in this particular form. So they are kind of orthogonal to this interaction. I'm not writing them down here explicitly because all the bounds that we can derive is for this particular interaction, this phi square box k phi square interaction. And these bounds are completely independent of the presence of these other interactions. So, and mainly because they are in some sense orthogonal. So the goal, as I said before, is basically to find out necessary statements about this effective field theory. And finally, as I said before, flat space limit is basically gives me the flat space effective field theory. So these are all the assumptions that I'll make throughout this lecture. Any question? Okay. So we start with this effective field theory in ADS, and as we discussed in the last lecture, there is a dual CFT D-1 description. And the kind of question that we are going to ask is basically that's related to the general idea of swampland, which is the idea, Pfaffer's idea that the space of, if this is the space of all effective field theories, only a subset of them can be UV completed. And the rest of them, they're in the swampland. So that's the general idea of swampland. So what we are going to do, we are not going to find out when this S effective can be UV completed, but generally what we do in Bootstrap, we can find out which effective field theories are definitely in this swampland. So basically, as in any Bootstrap system, we can only rule out theories. And we are actually going to answer the dual question. So that's basically the question. When does this scalar EFT doesn't not come from a UV complete theory that is dual to a CFT obeying the CFT axioms. So that's the dual question that we're going to address. Any question? Okay. So now we actually know what do I already know what do I mean by CFT T-1 obeying the CFT axioms. So what that means is CFT correlators necessarily satisfy some consistency conditions. And we derive this condition in lecture 2. Let me actually, just for clarity, let me actually briefly review what we did last time. So this is the picture that we had last time. Let me just copy paste it. Okay, so this is the correlator that we discussed last time. So this is the Reg Equivalator. Actually, for simplicity, let me just write down this as a function of eta and sigma. So this is a Lorentzian correlator, which we are looking at the limit sigma goes to 0, which is the Reg limit that we discussed last time. And there is also the second correlator, G0 eta sigma, which is completely determined by the Euclidean correlator. There is no branch curve or anything. So these are the two correlators that we studied last time. And this is a Lorentzian correlator. As you can see here, some of the operators are time-lag separated. Now, the thing that we constrain is this subtracted correlator, which is the Reg correlator, the full Reg correlator minus the Reg correlator for the free scalar theory in the bulk. And the particular type of correlator that we constrained had the following form. So this is the real part, and the imaginary part can be expanded as follows. Up to small corrections which can be ignored. Which can be ignored in the Reg limit. And this expansion is valid only up to some small parameter sigma star, which will play an important role today. This sigma star will play an important role. So the fact that the dual CFT obeys all the CFT axioms implies some consistency conditions. For example, this CLs should be positive. The second condition is the monotonicity condition. And the third condition is this log-convexity condition for L greater than equals to 2. So now what we have to do, we have to compute this Reg Equivalator for the CFT, which is dual to this scalar effective field theory that we wrote down. And that can be done very easily. So we actually know all the tools for even from like 20 years back. So the Reg Equivalator at tree level, so basically it's even the subtracted one because we are subtracting the identity exchange diagrams. It's basically given by two terms. A tree level exchange diagram. This is only when you have phi cube interaction. So this is a phi cube, obviously. And the second diagram is a similar one, but it's a contact diagram. Where these are derivative interaction. And when we do this computation, is to see that you get exactly this form. So that's a fact about any scalar effective field theory in ADS. They have this expansion, the Reg limit. So I'm not actually going to discuss how to compute these contact diagrams because they are well studied, and these are just some ADS integral. So and they look kind of complicated, but if somebody has enough motivation, they can always compute these diagrams, at least in some limits. So these are just some technical things, and in Reg limit, actually, these diagrams does simplify. So if you want to know exactly how to compute them in Reg limit, you can look at this reference. Okay, so now what do we get if I do this computation? So let me write down the effective action again. So from this effective action, we find that at tree level, this CL coefficient has the following form. There is an overall factor which does not depend on the level L, which is just an overall factor, so you can completely ignore that factor. It will not be important at all. A known function of eta, some part of our radius, times mu, where this is the mu, times lambda L, when L is even. So there is a proportionality relation. This overall factor K is not important, so I'm not going to write it down here. This F function, it's not very important for the purpose of the lecture, but just for the sake of completeness, let me just write it down. It's an integral of the harmonic function in hyperbolic space. And again, this integral can be computed, but the thing that will be important at this point is basically this is positive when eta is between 0 and 1. So this is one of the important equation. So now, as you can see, this is only when L is even. So this is only when these interactions. This is only for interactions like phi square box square phi square box 4 phi square, things like that. So what happened for odd interactions? So things like phi square box q phi square, things like that. So they always come as correction terms. So they will give you something like this. So for any L, this has a correction which is L plus 1, but they are always suppressed by higher power of R radius square. Something like this. Probably some other one number in front. Yes. So these terms, so the odd interactions, they are always suppressed. So one consequence of this fact is basically this analysis will not give you any constraint on interactions such as this. So all constraints that will derive, they are for even interactions. Before I move into deriving bounds, are there any questions?
Sorry, Sunil, I just came a little late. I forgot the timing. So eta, what was the eta was the CFT variable. How did you map it to the? How did you get it to the gravity? What exactly is eta from the gravity perspective?
It's basically like it's a quantity of the dual safety. So it's basically like when I compute things like this kind of diagram. So it's basically we are fixing the boundary points. So that's where eta is. It basically one way to think about eta is basically it controls when how fast these 2 points, let's say, they are approaching the light cone of each other. So
I see.
for example, is eta going to 0 limit is basically the light cone limit.
Okay. Okay.
So it's basically at this point you can just think of that as a parameter. Like basically we are going to tune eta such that we get the strongest bound. Okay, now we're going to derive bounds. So first, when we look at this expression, so everything in this expression, they're positive other than this quantity. This quantity. Everything else are positive. So the positivity of the CL coefficients now implies, so the first thing we derive is the fact that lambda k is positive for all even k greater than or equals to 2. So that's the first constraint. The second constraint, this is basically the second constraint is basically the only thing that we can say about these odd interactions. So if one of lambda k is 0 for some even k greater than or equals to 2, then all lambda k are 0 for all even k. So if one of the even interaction vanishes, then all of them must vanish. And interestingly, the same thing is true. The same is true for all odd k interactions as well. So basically, that means if one even k interaction vanishes, all k interactions must vanish. Even or odd does not matter. So the converse is not true. Like not true. If one odd interaction vanishes, that does not mean all the even or even anything else should vanish. But if one even interaction vanishes, everything should vanish.
Sorry, Sandipan. In your last slide, you related lambda k to CLs, right? Lambda to CL.
I like that.
Lambda L's to CL. So last time, was there any result for CL that 1 L vanishes, or if I might have forgotten?
Yes, yeah. This follows from CFT. So basically, in the last lecture, we had something like this. This condition was there. This condition. But if you remember, CL was some integration of a positive kernel with some power of something like this. So let's say one CL, let's say C10 vanishes. Then since this is a positive positive integral, this must vanish everywhere. So if this vanishes, then it does not matter what L you choose. For any L, you should get 0.
I see. Okay.
So this follows from the dispersion relation that from the CFT side. Yes. Okay, so this this statement that I just mentioned can be alternatively stated as follows: all the lambda k coefficient, even or in the case of even interaction, they are strictly positive. For even, for odd, they are non-zero, and obviously the possibility that when all the interactions are vanishing, so that you have like a free theory, that must be included. So the overall coefficient mu, we take that to be greater than or equals to 0. So mu is this factor over here, the overall coupling constant. So basically that means if you want to turn off one interaction, you basically have to turn off this whole set of interactions.
Sandipan, sorry, just to understand, this condition on CL followed from some analyticity property in the lower half plane or something, right? In your CFT analysis. So I understand that because of a map you are able to get it, but is there an independent argument here that why should such analyticity argument or some such argument, why should one lambda k vanishes? Then is there, sorry, all I'm asking, is there an independent argument for this also in the gravity side?
You mean like from the flat space analysis?
Yeah.
Yes, I'll talk about that. Yes, there is a way to actually derive at least like most of them. So this, let's see. I'm not sure how to derive this particular statement about the fact that if one even interaction vanishes, even all the odd interactions must vanish. I don't have an argument for that in flat space, but for the rest of the constraints, I have some other argument as well. And those arguments are actually known for like quite some time. It's just nobody actually wrote them down in this particular fashion.
Okay.
Now let me move on to the third important observation. So now if I look at the Reg Equivalator of the dual CFT, for the CFT which is dual to the scalar effective field theory in ADS, I see the following fact. So the Reg Equivalator is actually a function of not just sigma, it's basically a function of sigma times R ADS square. And this is something that we observe just from evaluating Witten diagrams. So that means, if you remember, let me again highlight this fact. So if you remember, we had this cutoff scale. So basically this Reg expansion is valid up to some cutoff scale, sigma star. Now, from this fact alone, we know that sigma star must be proportional to 1 over R radius square. So it's basically, if I start with the same effective field theory, if I just tune R radius to be, let's say 1.1 times the old R radius, so nothing should change physically. So sigma star basically will just, it will be just rescale, will just be a rescaling of the old sigma star. And this is the relationship that it must satisfy. Why this is important? This is important because that means this quantity R star times R radius square, this is independent of the ADS radius.
So when you write 1 over r radius square or 1 over r radius, you actually have an L Planck which is 1.
In this case, like this is there is no dynamical gravity. So basically,
that is okay, but then isn't sigma a dimensionless variable? How can you scale it by a dimension full?
I'll come back to that. Yes, that's a very important point. So that means basically there is some mass scale hiding in this expression. So so this quantity, as I said, sigma star times r radius square. So basically this depends on this intrinsically depend on the UV theory. So basically, as Anindya pointed out, so that means I can define some mass scale from this expression. So this M is some mass scale which has information about the UV theory. So this is, I'm going to take that as a definition of the EFT cutoff scale.
But Sandipan, last time you had sigma star to be bounded by delta gap, right?
So that basically this is the, like, I just wrote it down. Like I did not explain why that expression should be true. So this is basically the reason why it was sigma star was like 1 over delta gap square, because this scale M, it's the EFT cutoff scale. So M times R radius is basically delta gap.
So so there was no argument independently in the CFT. So
no
argument comes from here.
Yeah, this is the argument. Yes, yeah, that's right.
In the CFT, sigma star was something like, you know, in the expansion you could believe only up to sigma star or something, if I remember correctly, right? So
yeah, that's like that expansion must not be true when you take the limit sigma goes to exact sigma goes to 0 limit, because it will blow up, and Reg Equivalator cannot blow up. Right. So that must be valid up to some scale. So the sigma star is like definition in that way.
And from there, from that analysis, it is not possible to find out how sigma star depends on various things from that analysis, just from the CFT.
No. From that analysis, so that's basically like it's a statement about the validity of the expansion. So from that alone, if I know all the CL coefficients, probably then I know, because then I can find out when the sum converges, things like that. But in general, there is no way you can say anything about sigma star just from that formal expansion.
Okay.
So this is basically like we are defining this cutoff scale directly from CFT. So, and obviously, like if you just give me some effective field theory, I have there is no way I can define an exact cutoff scale, because that will require me to know the exact UV theory. So you can like, there are many different ways you can define the cutoff scale from the scattering amplitude that I'll discuss. So this is basically, this definition should be related to all the other definitions by some rescaling. That's it. Like there should not be any other thing that you can do. It's always like whatever way we define the cutoff scale, it's basically should be related to any other definition by some other one rescaling.
Okay, thank you.
But some of the bound will depend on this definition. Some of the bound will not depend on this definition. For example, the positivity condition, something like this, it does not depend how you define your cutoff scale. These are valid irrespective of the definition. Okay, now, so we had a statement like this before. Now, if I just plug in CL for all even L, so now we can just plug in our result for the dual effective field theory. We find something like, and now actually I have to make sure of something. So when for all these bounds, I'm taking the mass square of the field to be strictly positive. I'll discuss the massless case later. So this means basically since the R radius is large, so that means basically the corresponding delta, which is roughly m times r radius. This is also large. So whenever you have strictly positive mass square, the corresponding delta is always large in the large r radius limit. So these bounds are particularly for non-zero m square. We can just compute the left-hand side here. From here, I get the condition that lambda k plus 2 over lambda k. And actually, the strongest bound is obtained when we take take eta to be small after taking the Reg limit. So that's where you get the strongest bound. This is we get this particular expression. And if you look at our definition of the cutoff scale, this is just 1 over m to the power 4th. So this is the second important bound. But unlike the first one, this obviously depends on the definition of the cutoff scale m. However, whatever definition of the cutoff scale you use, so basically this inequality must be valid only up to a single rescaling. So it does not matter what cutoff scale you use. There is always some rescaling of the cutoff scale, which will make this valid, which will make this bound consistent with the definition of your cutoff scale. But this particular constraint has important implications. So what does it say? So let's just start with this interaction. Plus, let me write down all the other even interactions in this particular form. So I'm not writing down, I'm just ignoring the odd interactions for the moment. So this condition basically telling us that this C4, C6, they should be between 0 and 1. So this is basically not just this, like all the other even interactions. So basically, it's a derivation of the fact that higher derivative interactions must be suppressed by the cutoff scale with order 1 coefficient. But unfortunately, we don't have a similar argument for odd interactions. I'm sure there is some more sophisticated argument which one can make to actually constrain these odd interactions as well in exactly the similar fashion. But at least this particular analysis will not tell you anything about the odd interactions. But at least for even interactions, we can derive the expected fact just from the framework of effective field theory alone. Now, finally, I have another bound, which is kind of surprising, but since it's nonlinear, but it follows from the third condition, which when we write down in terms of the EFT coupling, has this particular form for even k greater than 2. And as you can see, again, this does not depend on M. So how do it does not matter how you define your cutoff scale. This is always valid. And this condition is basically the log convexity condition. This is also sometimes known as super convexity condition. The reason is you can apply this condition iteratively to show the following. For all even k satisfying this ordering. So this is just like the regular convexity condition, only difference is that now you have this log. That's why it's called log convexity. So actually this is stronger than the convexity condition. So in the sense that any function which is which is log convex is automatically convex, but all convex functions, they are not log convex. So this is stronger than the regular convexity condition.
So, sorry, Sandipan, you had a previous condition which was CL plus 2 by CL or lambda k plus 2 by lambda k is equal to 1 by m to the 4, right?
Mm-hmm. Yeah.
Using that also, you will get some sort of a bound. And are these two consistent or they are two separate?
Yeah, like I'm just like, if you use this iteratively, so basically like you start with like 2, 4, 6, then like you go to like you use like relation for 4, 6, 8, things like that. You can use that iteratively to get something like this. So they basically they are equivalent.
No, so this log convexity, I understand. I was talking about the previous, you had another bound which was like lambda k plus 2 by lambda k is equal to m to the 1 by m to the power 4, right?
Yes, yeah, that one, yeah.
So, I can try to use this as this is an inequality though, but I can try to use it to get a bound of the form, the next thing, I just multiply appropriately, like relate lambda k plus 2 to lambda k and lambda k plus 2 to lambda k plus 4. Are these things are consistent with each other?
Yeah, they're completely independent actually. So what I mean is basically like, let's say I just take the convexity condition. All it says that it should the lambda case should be a log convex function. So, but a log convex function can actually increase or decrease. So the other condition basically telling us that it must decrease. Like we have to pick the decreasing function.
I see. So these two conditions are not fully consistent with each other. It will restrict further, or sorry.
Yeah, they basically impose different restrictions.
They impose different restrictions, and you'll pick up which I see. Okay.
Yes. Yeah. So, for example, like it's possible that a simple example is, let's say, I don't want to say something which is wrong. So it's possible to like violate one, not the other one. Yes. So that in that sense, they are completely independent.
I see. But then, if I violate one, then I cannot have a consistent theory, right? So
But like,
I need to satisfy both, right? I need to satisfy both, or
yeah, you have to satisfy both. And like the point is, satisfying one does not guarantee you that the other one is satisfied.
Yeah. So it will just give more restriction. That's all it means.
Yes. Yeah. These are complete. Yeah. They are independent restrictions. Yes.
Okay.
Any other question? Okay. Let me now make just one comment about the flat space limit. So the flat space limit is taken the standard way. I take R radius to be large. We take delta gap, which is basically 1/square root of sigma star, to be large as well, but the ratio is fixed. And this gives the cutoff scale. So this is how we take the flat space limit. And as we discussed in the first lecture, since since Reg Equivalators, they basically describe high energy scattering dip inside ADS. So these constraints, this positivity, monotonicity, and log-convexity conditions, they should be valid even in the flat space limit. So another way of saying this is basically all these bounds, they should not depend on curvature of the spacetime. Now, as Sachin asked, can we derive similar constraints directly in flat space, just studying the scattering amplitude without going into ADS and going to the dual CFT description, without doing anything like that? Can we find these constraints? The answer is yes. And it's basically what Adams et al. Did in 2006. It's basically exactly that. And this argument is valid for mass square greater than or equals to 0. So note that now this contains the massless case, the flat space argument. So this is a flat space argument. So the standard assumptions are as follows. I'm not going to discuss them today anymore because we discussed them in details in the first lecture. It's basically the same assumptions. If I just assume this conditions about the full amplitude, even in the UV, from here, it's easy to derive a dispersion relation for all even lambda case. And it's as follows. It's just a generalization of the famous phi square box square phi square bound. So it's the forward amplitude divided by s to the power k plus 1. And note that there is this m square. which at this point does not have to be the same m square that we had from the CFT analysis. So this expression is something that can be easily derived from these 4 assumptions. And from this dispersion relation, you can derive the same set of conditions. The last one is basically a Cauchy-Schwarz inequality. So, and note that this is the m square that you get here. So this is basically exactly the constraint that we obtained from the CFT analysis. And not only that, so now this identification gives us some meaning of the cutoff scale that we defined from the CFT side. It's basically identical to this cutoff scale. So the cutoff scale, this cutoff scale m should be regarded as basically the lightest massive particle exchanged in the UV. Or another way of defining it is basically the energy scale at which the imaginary part of the scattering amplitude starts becoming non-zero. So there are many ways you can define the cutoff scale. So basically, the CFT cutoff scale that we define, the cutoff scale that we define from CFT analysis, this can be identified with this definition of the cutoff scale from scattering amplitude. So since
sorry, Sandipan, it looks a bit in this case, it's just opposite of CFT, or am I like in your CFT the cutoff was up to sigma star, and beyond that you do not wanted to apply things, right? And here actually below m square you don't want to apply, you want to everything comes above m square, right?
Yes.
M square to infinity range is what map to 0 to sigma star, or like up to sigma star there, or is the opposite?
It's the opposite. It's basically so 0 to m square. Let's see. I don't want to say anything. So no, m square to sigma. So this range in the CFT side, it maps to something like let's see, 0 to sigma star. Yeah. So this so the m square basically maps to sigma star.
I see, but in that case, as you said, like beyond m square, there will be branch cut appearing, etc., etc., and below, so it's just the opposite. Like there, beyond sigma star, maybe you don't know what are happening, whether it is analytic or not below, or here beyond m square, you know, this is not analytic.
We know that, like so basically we know that above m square we don't know the amplitude, but we know that basically that this quantity is positive, things like that are known. So below m square, like much below m square, we know how to compute the amplitude from the effective field theory. That's why we can write down this contour integral, and we can find out these coupling constants.
Oh,
the same.
I see. This is like a sum rule kind of thing. Exactly. You're relating the something below to the higher.
Yes.
In CFT, sorry, in CFT, was it similar? Did we relate something?
Yeah. So the CFT sum rule is basically like you're relating some UV to some IR. For example, as I said before, so in this particular CFT range, so that the CFT expansion, that the Reg expansion that I wrote down, that's not valid, right? Because like that's valid above sigma star. But still, since we can relate that region with a region where the Reg expansion is valid, so we get basically some dispersion relation where on one hand I have coefficients of the Reg expansion, on the other hand I have some CFT correlator which I cannot compute, but I know they are positive.
I see.
It's basically they are almost analogous to each other. So you cannot map each step of one argument to the other argument, but like it's basically they are very similar.
Yeah, it will be very interesting to see the thing that we were also discussing last time. There is this map from correlation function to the amplitude. And then you have, if this relation that you have in the correlation function directly goes over to this kind of constant on the amplitude.
Yeah. As far as I know, at least like these two dispersion relations, there is no, so far I don't know of any relation. Like that's not because there is no such relation. It's basically like I don't think anybody tried.
Okay.
Okay, now one important observation, since like we get the same set of bounds from the flat space analysis, so that basically says that, and this is true, like for the CFT analysis, as I said before, the bounds are valid only for the massive case. So it's a strong indication that this set of assumption, they are valid for massive external states. Seems like the validity of these assumptions are not, there are some, they are not completely rigorous. So this is a very good evidence in favor of this assumptions, at least for massive external states. And as you know, for massive external states, things like crossing, even analyticity in some regime, they are better understood. So probably this is not a surprise that in this particular, for the massive case, there is a match between the CFT bounds and the flat space bound. But interestingly, the same is not true for the massless case. In fact, a flat space effective field theory of a massless scalar field is basically, there are multiple ways that you can get a massless flat space theory from some ADS theory. So for example, I can take M to be finite first, then take RADS to infinity, and then take the limit M goes to 0. So this is the first limit, this, the first limit, then this. In this case, you recover the same set of bounds as the massive case. So there is no a difference between the massive and the massless case, obviously, because this is basically the limit that we are taking the limit that M is non-zero, and then we are taking, at the end of the day, we are just taking the limit that M going to 0. But this is kind of, this is not the right way of doing it, because obviously there is a discrete difference between the massive case and the massless case. Another thing one can do is basically just take M squared to be 0 to begin with. So that's a well-defined thing one can try. More generally, what one can do is basically one can take our radius to infinity and M to 0 at the same rate, keeping our radius times M fixed. So that basically gives you some delta, which is order 1. So these two cases are, the first case is kind of trivial and it's basically the same as the previous case. The next two cases, they are very interesting. So this is basically delta equals to d minus 1. But that's the dimension of the CFT. So now what happens for these two cases? So basically we get almost identical constraints, but they are not exactly the same. So this constraint remains the same. This is, there is no change here. But the other two constraints, there is a modification which is kind of important. So basically, what happens, just take the old one, and basically you have to rescale lambda k by a known factor. So this factor, as you can see, it depends on delta and also the order k. So basically, like in the old set of bounds, just replace lambda k by this quantity, where I can write down n, but it's not going to be very illuminating. But just for the sake of completeness, let me write down this factor, just at least just to show you that this factor is exactly known. As I said, like this factor is not very illuminating, but like this is a given a delta, this is given a delta and k, these are just numbers. So because of this rescaling for the massless case, these are actually strictly weaker than the bounds for the massive case. So what does that mean? One possibility is basically the assumptions that were used to derive the flat space dispersion relations, which are basically these assumptions here. So these assumptions here, probably it's possible that they are not valid for massless external states. So that's kind of interesting. In fact, when we take the limit delta goes to infinity here, we recover the old, we recover the flat space bounds. So basically, for in this limit, the flat space assumptions are valid. But for any finite delta, we get strictly weaker constraints. So probably the way one can interpret delta is basically it is a measure of the breakdown of the flat space assumptions. So the massless case is very interesting. There is another possibility though. It's since we are obtaining weaker constraints, it's completely possible that this is a fault of this particular analysis. It's possible that there are stronger bounds that can be obtained from some more sophisticated setup, but it's obviously it's a possibility. So all I can say is probably the exactly massless case should be studied more carefully.
Sandipan, I have a naive question for you. So I understand what it means to take delta phi to infinity. I've always been a little troubled when you say that m, which is a dimension-full quantity, you're taking it to 0 or you're taking it to infinity. So I believe the correct way of thinking about it is that there is a fundamental length scale, maybe length Planck or L Planck, that is there, which you're holding fixed and you're not doing anything to that. And then when you say that m goes to 0, that you literally mean that m times L Planck goes to 0, or r divided by L Planck goes to infinity. Is that right? I mean, it doesn't make any sense to say that a dimension-full quantity is taken to 0 or infinity.
No, but like you can always have so there is a difference between the exactly massless case and the massless limit.
Mm-hmm.
A field can be exactly massless, and for example,
no, I agree that m square can be exactly 0. That I don't have any problems. It is the limits. When you say that you're taking the limit.
So like going to infinity, like we are actually never taking m squared to infinity actually. So m squared is.
I mean, it doesn't matter. Even when you say that r goes to infinity, it seems to me to be a very dubious statement, because it depends on what units I'm measuring my things in. I mean, suppose I'm measuring my units in microns. Something that looks like infinity in micron scale might not look infinity in some galactic unit scale.
Yeah, that's right. So okay, yeah. So the precise statement is, whenever I say r radius to infinity, it's basically always in terms of the cutoff scale. So this quantity is large.
Yes.
So the order of limit is we are in this case since there is no dynamical gravity, we always take m Planck to infinity first. Then we take the limit that r radius times the cutoff scale is large. So that's the order.
And there is another little m, which is the external mass. So when you say that m goes to 0, it's a little m by capital M that goes to 0.
Yes. So this is always smaller than r radius times capital M.
Right. Yeah. Good. Thanks. Yeah.
That's right. So the order of limit is very important, and actually this is going to get a little bit more confusing when I make gravity dynamical. But actually, probably that will actually clarify more things.
Okay.
And since actually we can actually move on to the dynamical gravity part. Okay, so so far, as I said, the gravity is non-dynamical. It's just a background, but conceptually that's kind of unsatisfying, because the whole idea of Swampland was introduced to study or to discuss quantum gravity. So in that idea, the UV complete theory is the theory of quantum gravity. So inclusion of gravity is kind of essential in that picture. In any case, like gravity is there. There is no way we can ignore it. So whatever framework we choose to use, it would be nice if it can handle dynamical gravity. And it turns out that inclusion of dynamical gravity, let's see. It turns out inclusion of dynamical gravity is just a straightforward generalization. Of the previous analysis. So now the effective action is basically the old effective field theory action, plus now we have the Einstein-Hilbert term with a cosmological constant, negative cosmological constant, the standard effective action. So what happens in dual CFT? So in the dual CFT, the central charge CT, which is basically the coefficient that appears in the TT 2-point function. So this is the largest quantity, then delta gap, and both of them are large, but both of them are finite. So they are finite but large. So the stress tensor can no longer be ignored. So the previously, when you take the limit C, the central charge is infinitely large, it basically decouples the stress tensor. But in this case, we should consider stress tensor in the CFT analysis. So now, again, I can compute the Reg Equivalator. I get, at tree level, I get no gravity result, which is basically the other two, the previous two Witten diagrams, plus now I have an additional Witten diagram. So now we have to compute this extra Witten diagram. That's it. The CFT theorem that was derived in lecture 2, it remains exactly the same because it does not care about it does not care about the details. It's basically it's a general theorem. Now, when I do this computation, I again can compute the CL coefficients that appear in the Reg expansion. So we again get the no gravity result. That part should be there because it's the sum of the first two Witten diagrams. Plus now I have another term from gravity, which is, this is some numerical factor, which is not important. Again, there is some known function of eta, which I'm not going to write down here. That's not going to be important. Now, and this is obviously proportional to J Newton. And the important part is this term. So there is a Kronecker delta. So the gravity term only affects C2, but C4, C6, all the other things, they remain the same. So basically, for most constraints, they should remain unchanged when you include dynamical gravity. So bounds.
Sorry, Sandipan, I missed something. So from the CFT perspective, so you said CT will be just very large, right? From the
yeah.
And how does it change your analysis? Sorry, here you are from the gravity side, you are finding out what would be the change. From the CFT perspective, sorry, I missed. What exactly is the change in your analysis?
So the theorem that I discussed in lecture 2, that theorem did not know whether like the stress tensor decouple from the low energy spectrum or not. That analysis is a general analysis that does not care about the details.
Right, right.
So all the positivity condition of CL coefficients, all the bounds that for CL coefficients, they should be the same because it was a general analysis.
Right.
The only thing that changes is basically the actual value of these CL coefficients when you input gravity.
Well, actual value meaning from the sorry, you mean the relation between lambda and CL that changes?
Yes, yeah. By actual value, I mean like how you determine CL coefficients from the effective field theory. Like that relation is different, but the actual like the bound on the CFT bounds are exactly the same.
I see. Okay. Okay.
So the mapping is just different. That's it.
I see. Okay. Okay.
What happens to terms in principle which you can turn on, which look like R mu nu, del mu phi, del nu phi? Are they zero by for some reason?
This kind of form.
Yeah.
So in ADS, obviously you can keep this term, but so if in the flat space limit, it's basically like it's not going to.
Yeah, flat space it won't affect, but what happens in ADS?
You mean like this in this identification between CL and?
Yeah.
Let's see. Is it going to change? So basically, what all it will do, it will basically going to change this 3-point interaction.
Yeah.
So if you do that, but actually, I don't think it is going to change anything because like the graviton scalar 3-point vortex is completely fixed from symmetry. So this can give you an overall change, like of p-factor probably, which will be like 1 plus something that's suppressed by 1 over r radius.
Right.
But other than that, like yeah, it should not change anything.
Yeah, I see. Yeah. Okay.
Yeah, because like this might be important when you have spinning field, because then this term can actually change the 3-point vortices.
Yeah.
Yeah, the scalar case is actually very simple in that regard. Okay, the bounds are.
So, sorry, I'm very naive. I should know this. The loops are never like that. Like in the CFT side, they are not important, or they are suppressed, or what happens to the loops?
Yeah, this is entirely for the tree level effective field theory. So I'll mention this later probably. Like when you include loops, again the CFT theorem, it remains the same. Like it does not, the CFT theorem does not know anything about like loops or tree level, anything like that. It's a general theorem. Right. So if you include loops, basically then you have to include loop contributions here. So that will basically change this mapping between CL and the coupling constants. But so basically, so far everything is computed in the limit where in the leading order in mu and g Newton.
I see. Okay.
So this is basically a constraint on the tree level effective field theory. So the first bound when we have dynamical gravity is that all bounds remain the same for lambda k with k greater than or equals to 4. So everything with like 4. So all this any bounds that does not involve lambda 2, they remain the same. So the only thing that changes whenever you have a bound with lambda 2, Now there is a shift. So just take the old one and there is a shift by some positive prefactor, numerical prefactor times pi g Newton r ADS square over mu. So basically, whenever you have other lambdas, they remain the same, but for lambda 2, there is a shift. And actually, the shift is very easy to understand why there should be a shift for lambda 2. Let me explain that. So without dynamical gravity, there is the relation that lambda 2 is positive, no gravity. Obviously, after this, so when we have gravity, this becomes something like this because of the shift. Times some, this is a numerical factor, which is non-numerical factor. And no, this is known and positive. So the way this should be understood is basically this is gravitational time delay. Just to remind everybody, so this is the coefficient of phi square, box square, phi square. So the fact that lambda 2 is positive when there is no gravity, in certain scenarios can be understood as a causality constraint. So when lambda 2 is negative, there is some kind of time advance. So that's why lambda 2 has to be positive. Now, when you switch on gravity, gravity always introduce a time delay. So because of that, now you are allowed to have a little bit of time advance just from the non-gravitational physics, because then because of the gravitational effect, you'll always get some time delay, and together the entire thing can give you a time delay, but not an advance. So that's why this kind of relations, they make sense. But there is something that can start to bother you when you look at this expression for a while. It looks like for large RADS, this quantity on the right hand side, it starts to grow fast because of this RADS square factor in the numerator. But obviously, that's not. So it does not actually blow up when you take the flat space limit. The reason is as follows. I can rewrite the above expression in a different form. Some order 1 number, delta gap to the power d, central charge, mu to the power d. So as I said before, in the safety side, we are always taking central charge to be large first, then we are taking delta gap to be large. So this quantity on the right hand side is always small, even when our ADS is large. So another way of saying this, as Anindya mentioned before, so the order of limit, the way we should take the flat space limit is as follows. So this is large, but this is smaller than the scale set by G Newton. So this is the actual flat space limit. So for now, what happens if I take this flat space limit? So if I take this flat space limit as I just explained, all I can say is that the right-hand side is negative but small. But I actually don't have a precise numerical definition of in flat space because of this RAD square sitting there. I don't know what to use to get an exact numerical factor there. So what does that mean? So that means, so when gravity is dynamical, all I can say is lambda2 is greater than some number minus, which is minus c, where c is small, positive, and because we cannot find it exactly, this suggests it's a theory dependent. But that's fine anyway, because there is always the cutoff scale. So the fact that C is small and positive, so it's non-zero, that's already a non-trivial thing that we learned about this effective field theory. And this is actually consistent with flat space result that we have for d greater than 4, thanks to Karen et al. From earlier this year. So what their result was valid for d greater than 4, but this is completely consistent with their result. But this is very interesting for a separate reason. The positivity of lambda2, the fact that lambda2 is positive when there is no gravity. So that fact actually led to the proof of the A theorem. So I can actually perform the same kind of analysis, but now we can keep gravity dynamical. Then again, we should get a lambda2, which is basically a UV minus a IR. But when gravity is dynamical, because of this expression, it looks like the A theorem should not, in general, should not be valid. So this is a very interesting thing. So does that mean the A theorem is not valid when gravity is dynamical? I don't know the answer to this question, but this is certainly a very interesting question that one can study. So let me just let me end with some comments.
Sorry, I didn't understand the last statement. So purely from the CFT side, so what is the exact comment? You're coupling the CFT to gravity, and then you're asking whether the A theorem is valid in that theory, or are you asking that CFT has a stress tensor? And no, but that is not true, right? I mean, you're asking the former question. Is that what you're asking?
Yeah, I have some, let's say, UV fixed point. I take that CFT, I couple it to gravity, then I make some either explicit breaking or some spontaneous breaking of the CFT.
Yeah, but if you're coupling to gravity, then the notion of central charges becomes ill-defined, right? I mean, you cannot define the C and A. Because there is no stress tensor in that theory, right? I mean, there's no conserved stress tensor.
But I can still talk about the stress tensor of the CFT, just the CFT.
But is that a well-defined?
Yeah, probably so the fact that there is no A theorem probably suggesting that all the steps are probably more subtle. There might be this is basically, I'm not saying that A theorem is not valid. It's basically the entire picture has a lot, must have some kind of subtlety. because
Yeah.
like just from a physical perspective, like even if I like don't consider dynamical gravity, it's already there. We live in a world where gravity is there, and there are quantum field theory which has like UV fixed point, IR fixed point. Like these two pictures should be consistent with each other.
Right. But of course, I mean, that sort of defeats the philosophy that gravity is somehow emergent in the sense that you're supposed to have a purely conformal field theory, which is supposed to describe gravity in one higher dimension. In that
Yeah.
sense, yeah.
So the thing I'm talking about is basically more like kind of like quantum field theory in curved space-time, not more like
Right. No, I understood the point. Yeah. Okay.
gravity. Yes.
Yeah.
No, this is something that like I'm planning to think about at some point, like, because this is kind of interesting. Probably like there might be other explanations. For example, it's possible that since you turn on gravity, like the thing that measures number of degrees of freedom is probably not A, it's A plus something else. So like that quantity should be positive, not A. Like, yeah, like physically many things can happen actually. Okay, let me now make a couple of comments. So first comment is all the bounds for k greater than equals to 4. Okay, before that, in first lecture, I mentioned that the bound on phi square box square phi square, it's basically a semi-classical bound. In the sense that you can derive the same bound from even from the classical theory, but just by studying some fluctuation of some background solution. But the same is not true for higher point interactions for k greater than or equals to 4. So basically, these bounds are basically quantum bounds. Like there is no at least I don't know of any classical argument which will lead to the same set of bounds. So they are truly quantum bounds. The second point is about saturation of this ADS bounds. So let's say I have some ADS bound, which is something like this. X is strictly positive. So now when I take the flat space limit, I should not conclude that in flat space, X should be strictly positive. The required conclusion is X should be X is allowed to saturate the bound. The reason is, it just as an example, let's consider that I write down X as this expansion, some X naught plus X1 with some RADS factor and similar higher terms suppressed by RADS, some higher part of RADS. And the fact that X is strictly positive in ADS only tells us that X naught has to be greater than or equals to 0. And in the flat space limit, this is exactly what you will recover. So basically, this is kind of obvious, but still it's an important point that whenever you have some strict inequality in ADS, and if the analysis is valid, even if when you take the flat space limit, you always should interpret that as a bound which can be saturated. Third point is about the phi cube interaction that I mentioned in the beginning. So let's write down the phi cube interactions as follows: alpha phi cube, where the dimension of the mass dimension of alpha 3 is its mass about 3 minus t over 2. So what it means is basically now, because of the phi cube interaction, I'll have diagrams like this, or like similar diagrams, like this 3-point interaction will show up everywhere. It does not actually change our derivation of the bounds at all, because exchange of a scalar field in ADS actually does not lead to a Reg equivalator which grows in the limit sigma goes to 0. So the CL coefficients should remain unchanged even when you exchange a scalar field in ADS. So the bounds are not remains the same, but there is another subtlety that we should discuss. So whenever I have this kind of diagrams in the dual CFT, basically this quantity will always show up because we have something which is dimensionless. So if you have 2 vertices, it will be something like this. So basically, what happens is that in the limit of large R ADS, this quantity grows basically there is another way of saying this. When this coupling is large, when this coupling measured in our ADS is large, then basically there is a mixing. There is a large mixing between the scalar safety operator O, which is dual to phi, and spin 0 double trace operators. So basically, the actual primary operator is not O, but some mixture of these two set of operators. So that's why in the safety theorem that we derived, there basically O was a primary operator. So basically that theorem can break down if O is not a primary, not a real primary. So basically, that means this interaction can actually make the analysis to break down when RADS is too large. But this is obviously, this is not actually a real problem. This is a technical problem which can be avoided by taking the right combination of O and double traces. But in any way, what you can do, you can bypass this problem by starting with a theory with Z2 symmetry or any such global symmetry such that this interaction is not there at all. Or obviously the second obvious resolution is the flat space limit should be taken such that our ADS is large compared to the scale set by the cutoff scale, but small compared to scale set by alpha 3. But it's not guaranteed that these two limits can be consistent with each other. So in that case, there is the flat space limit is problematic, and probably you should not trust the bounds in that case. Another point is that it's actually very easy to generalize the same analysis for multiple scalar fields. I'm not going to show you that, but like it's very easy to do. It's a straightforward generalization. And there are actually, when you have multiple scalar fields, actually there are new types of bound you can derive, which are completely different from bounds that we studied. For example, there can be bounds on interactions with, there can be bounds on odd interactions when there are multiple fields, and there can be interference bounds, which are completely nonlinear and complicated, but these are new bounds. And actually studying this kind of setup where there are multiple scalar fields, it is possible to actually derive new set of bounds for RG flows with some global symmetry breaking, let's say, where there are actually in the IR you have a theory of normal-Goldstone bosons with more than one field. So this is actually, this kind of things has applications. I already mentioned loops. So if you include loops, the CFT theorem remains the same, but then the identification between CL coefficients and the coupling constants become complicated, but in principle, the same kind of analysis can be done even when you have loops. Spinning fields. Even for spinning fields, a similar CFT theorem can be derived starting from Rindler positivity. The statement is exactly the same. And for spinning case, the only difficulty is a technical one. It's basically the computation of the Reg Equivalator is more complicated, but in principle, it's exactly the same kind of setup and same kind of analysis. And actually, one of the motivation of this work was actually to generalize it to constrain for graviton amplitude. It's almost the same as what we have done here. So they are basically the coupling constant mu will play the role of the string coupling. But yeah, this is something which will be really nice to do at some point. And it's possible that stronger bounds can be obtained from numerical bootstrap. For example, like the kind of things that Karen Watt and company are doing, probably they can get stronger constraints from that kind of analysis. Any question or comment or anything? Okay, then let me just summarize and end. So the main takeaway is basically that at this point, we all should know that all effective field theories cannot be UV completed. The second point that I want to really emphasize is that EFTs in ADS provide a good alternative perspective to think about EFTs. One advantage of this framework is that EFTs can be constrained directly from safety axioms. As an example, we basically discussed scalar EFTs. And we showed that safety bounds implies that interactions such as this obey certain positivity, monotonicity, and log-convexity conditions. Important fact is for massive external states, all the bounds are consistent with the flat space assumptions that people use to derive constraints from scattering amplitude. So they are consistent with flat space assumptions. But the massless case actually I think this is more subtle, and it's very possible that for the massless external states, some of the flat space assumptions can actually, in general, break down, but this will require more analysis. It's kind of actually, I still find it kind of amusing that even after so many years, we can still say new things about scalar effective field theory, which we have been studying for so many years. And final point is for dynamical gravity. So when we have dynamical gravity, it only affects bounds involving phi square, box square, phi square. All the other bounds remain the same. Let me stop here. Thank you very much for the opportunity to give this lecture series. I hope that it was useful. And if there are any questions, please feel free to ask me.
Thanks very much, Sandipan, for a beautiful set of lectures. They will be very useful for us. You can continue discussing. I unfortunately have a meeting, so what I'll do is I'll make Parthiv host, and then you guys can continue discussing. I will also stop recording, and you guys can continue discussing.